So we're going to talk about the dynamics that goes into rotational motion. When we talk about physics, remember there's two main sections of physics. One is kinematics and one is dynamics. Okay, dynamics means forces. Okay, so the dynamics that we've studied so far have been basic forces. So the force of a rotational motion object tells us basically why this object is moving, right? Any type of force will tell us why it's moving. Forces can speed it up, slow it down, change directions. Forces are what put things in motion. But torque tells us basically how efficiently our object is rotating. Okay? How efficiently or how effectively this force is to put an object in motion. Okay, that's what you can think of torque as. When we're looking at forces and to get things spinning, we want to basically see how effective or how efficient that force is to put it into motion. Okay, because there's some instances when you want to start something in motion, whether it's spinning something or whatever it is, you might be pushing really, really hard, but that thing's not moving. Okay, you might have to readjust where you apply that force to put an object into motion or to get it spinning. Okay, that's what torque looks at. So our equation for torque is our T here, okay, equals R perpendicular times a force. Okay, and the reason we say it's radius perpendicular, okay, is because we want the radius to be perpendicular basically from the axis point or from the rotation point to where the force is being applied. Okay. So this perpendicular radius is realistically the distance from our axis point to the point where our force is being applied. Okay, hopefully those things are at a right angle. That would be the most convenient for us. That distance is also sometimes called the lever arm. Okay, the lever arm. And I want you to open up your book and read about the lever arm a little bit more because I think it explains it a little bit better than I do. So if you open up to page 218, I want you to start reading that paragraph. Okay, what happens when the force moves closer to the axis point? Okay, so we're going to start it over again. Our force is farther away, right? It's farther away on this wrench. If we move the force closer to our axis point, we have less and less torque, right? Our turns become less and less efficient or less and less effective as we get closer to that axis point. How many of you have used a wrench before? Okay, hopefully most of you, okay. You hold on to the end of the wrench and you turn, you'll see that you get a greater turn with the amount of force that you apply. When you move yourself closer, you can't turn as much, right? You have to reset that wrench more and more often if you're going to put it closer, if you're going to put your force being applied closer and closer to that axis point. Okay? That also should make sense with our equation because as our radius decreases, what happens to our torque? It decreases. Okay. All right. So we have it basically, let's try this one here actually before we move on. I apply 100 Newton force to the wrench at a position 0.20 meters from the axis point. What is the torque? Right, do we ever need to split that distance in two to make it the radius? No. Okay, because the radius is the distance from the axis point to our force, right? If we completed the circle here, that would be the radius. Okay, this is really as easy as it seems. Okay. Units for torque are just Newton meters because we're taking newtons times meters. Okay, simple enough. Very easy for problems that have a perpendicular radius and force. Okay. A different way that we can use to solve for torque, which I think might be more applicable to us, that might be a little bit simpler rather than using that lever arm, is to take the perpendicular force rather than the perpendicular radius, right? To split your force into components and use the force that's perpendicular to the radius that already exists. I think that's going to make a little bit more sense to us. We can use either version, it makes no difference, but this we would use force perpendicular times the radius. I think this is the one that would make more sense to us a little bit. So instead of having to complete the triangle with that lever arm and building ourselves kind of that imaginary triangle, we're going to be able to break down a force that's at an angle into its perpendicular and its parallel components, and we're going to be able to just use that perpendicular component. Okay. Sorry, if you need that, go ahead and put it down, but I'll show you an example of what I'm talking about here. Okay, let's say that I'm pushing upward here. Do we see why we're pushing upward? Okay, our force is going away from our object, right? That's how we draw a free body diagram, is away from our object. We are applying a force upward. We're trying to make this thing rotate in this direction. So when I break this force into its components, I would have a parallel component right here that's parallel to my axis of rotation, and I would have a perpendicular component. Okay? Usually when we draw it, we would draw it like this, right? Our parallel component would go here instead of there. I'm sorry, our perpendicular component. It makes no difference, right? This is still perpendicular. It still would be this radius distance away. Okay, but that's why I would use this method instead. I think it matches more what we've been doing in terms of forces by breaking it down into components. Okay, does this method make sense? Okay. Torque is still going to be radius times force. Okay, you can either use the perpendicular radius or you can use a perpendicular force, but you just have to understand they have to be perpendicular to each other. That's it. Okay. You can use this formula basically if you were unsure about which to solve for, right? The theta is the theta is going to be the angle between those two things, between the radius and the force. If you're unsure, you can use this formula, okay, and it will work. I still think it's going to make a little bit more sense conceptually for us to solve for the perpendicular component of our force and then take it times the radius, but if you're unsure, you can use this. Okay, let's go ahead and look at page 219. We're going to walk through example 8.8. Bicep muscle exerts a vertical force on the lower arm as shown in 14a and b. Okay, the radius is 0.5 centimeters. So we need to convert that radius first to meters. 5 centimeters would give us 0.05 meters. Okay, our force is 700 newtons. Okay, so to find the torque about the axis of rotation, right, we want to find that through the elbow joint. Is our radius and our force already perpendicular? Yes. Okay, so there's no need for us to even do any calculations with the components of that force because it's already perpendicular. So we would take torque equals 700 times 0.05. And that gives us, like our book shows us here, 35 Newton meters. Okay? I don't know why it says meter newtons. I just label it as Newton meters. Is that making sense a little bit? Okay.
Makes sense, but like, why do you do it?
Because we need the perpendicular component of that force. Right now, our force and our arm are not at right angles to each other. Here's our force, here's our arm. Okay. Is that 5 fingers? Okay. There's our arm. Okay, I know that. I'm not an artist. Okay, so our arm and our bicep, right, would be at an angle like this. We have to have the force that's completely perpendicular to that arm. Okay? So we want to find basically this little guy right here. So we would use sine of 60 degrees. Okay? I know this is a little tricky to visualize, but hopefully are we getting there? Sine 60, right? Because we want that perpendicular component. So we would take 700 times sine of 60 to get our force perpendicular. Okay, can somebody tell me what that is?
Is it always the angle opposite of the perpendicular force that you sine on?
Well, this is a tricky diagram, but most of the time it will tell you what angle the force is being applied at, and you would just use that. This case, it just drew both angles for us, and it was a little bit difficult to see. That's why we drew the whole figure. Okay. All right, what is that 700 times sine 60? 662? 606.2? Or did I make up the point 2? Okay. Then we take that times the radius, which is 0.05, and we get what? All right. So which of those forces would be the most effective? Which gives us the most amount of torque? The first one. When we just apply it at a perpendicular angle. Okay, we should see that in all of our examples that it's always going to be most effective to apply that force at a perpendicular angle. All right, try this one. Okay, we have our radius here. We have a torque. We have a force.
Me too.
Okay, so here's our example. We've got a force. We have to find force perpendicular, and we want to find that angle. Okay, but we can use, right, if we solve for force perpendicular, we're going to be using sine or cosine? Sine, right? So we can use that example or that equation that we got. Torque equals F R sine theta. Okay, because we're going to be taking force times sine of theta to get the perpendicular force anyway. We can do it in one equation here, and we're just solving for theta. Okay, so our torque, we were given 32.4. Our force was 232. Radius was 0.234 times sine of theta. Okay, so do that math to move those over. No. We agree? Yep. To find that angle, I did second sine of, I got about 0.597. Okay? Okay, seems simple enough? Okay. Now we're going to talk about net torque. What's the word net mean? Overall, good. So we're looking at basically if a system is balanced, that means it's not rotating one way or the other. Okay, think of like a seesaw here, okay, or a teeter-totter. That's a really common example for this portion of our chapter. Okay, if a seesaw is balanced, what's happening? When two people are sitting on a seesaw and it's balanced, what's that mean? Yeah, they're either even weight, or what happens if I I was sitting across somebody that's a lot lighter than me. What do I have to do, or what do they have to do? You have to, exactly, you have to move yourself to different locations along that axis point. That has to do with torque. Okay, whether you thought about that or not, it does. Okay? So, when we're talking about this system that's in balance and I'm sitting across from somebody that's lighter than me, I have to get my torque equal to theirs. Okay, so if I have a greater force of gravity acting on me, what has to happen to my radius? It has to get smaller, right? And if they have a lesser force of gravity on them, they need to make their radius bigger. Okay, so that has to do with the torque of the system and how those things are going to rotate. Okay, so this gives us kind of an equation here for net torque. T1 equals T2. And I actually kind of want you to rearrange this. I don't like how I wrote this out the first time. Okay, you don't have to put that one in there. I like to go like that. Okay, so F torque of one object equals torque of the second. That's what happens when a system is in balance. Okay, when it's not spinning one way or the other. If we're given a net torque that's not 0, then you could use this equation, and instead of 0 there, you would put in the net torque. Okay, does that make sense? But when a system is in balance, you would set those two things equal to each other. Okay, they want to balance on a 1.75 meter long seesaw. Where should they place the pivot point? So this allows us to place our pivot point here. Okay, we have to decide where the axis is going to sit. Okay, which is not realistic in a seesaw, but it happens. That's right. The force acting on them would be the force of gravity. Okay, so let's find each of their forces first. All right, now what do we need to do for the pivot point or their radius? What do we know about their radius? Okay, so let's think about this. What do we have to know about the sum of their radius? The sum of their radius has to add up to 1.75. So what do we do if we're missing both of these variables? We're missing radius of Shelley and radius of Anne.
This put one radius as x, and then the other one as 175
minus x. Perfect. Okay, so we'll pick one, make that variable either r sub a or r sub s. The other variable would then have to be 1.75 minus whatever that radius would be. Does that make sense? Do we understand why that has to be the case? Okay, so let's look at this. Our seesaw has to be 1.75 meters long. Okay, so they have to sit somewhere along this teeter-totter. Okay, so wherever we place the pivot point, let's say we place the pivot point there. This distance, her radius plus her radius, have to add up to 1.75 meters. Okay, so r sub a plus r sub s equals 1.75.
Yeah.
Okay, so if I am solving for r sub a, I have to know that r sub a also equals 1.75 minus r sub s. Oops. Minus r sub a.
No, you got the first time. R sub a, you got the first time.
I was right the first time. Okay. Essentially, though, what I'm trying to get at is that we can plug these variables into that equation and solve for one at a time, and then take 1.75 minus that variable to get our second radius. Does that make sense? Okay. We can put it as x. That was a good idea. All right. So I need 548.8 times her radius. Okay. Do you want to just plug that in as x, or would you rather it r sub something? Okay. That would equal the second force times 1.75 minus x. Okay, do we see where that's coming from? Okay. Mhm.
I had a question about that.
Mhm.
So when I did this, I saw since there were two people, and
Mhm.
divided by 2. I added up their weights and found what percentage each person had, and multiplied that number by 1.75, and I got that.
That would be.
And I got the same answer.
Oh, okay. That's fine.
Would it work on other ones, or like some of the different?
But this is rare because we get to place the pivot point.
Okay.
Normally, the pivot point will be chosen. It'll say one person is this many
Okay.
meters away, one person is this. But yeah, that was good.
Okay.
Okay, so that means that Shelley was 0.76 meters away, and Anna would be about 0.99 meters away. Okay, so the pivot point's not exactly in the middle there, or they have not located themselves at equidistances. Okay. Questions here? All right. That is going to be where we stop for notes for